The way we do this is using Newton's laws, really the second law, which goes as F equals ma, and then there's a counterpart for rotational motion, which goes as torque equals I alpha. So the way you do this is draw free body diagrams. So step 1, FBD or free body diagram. Then we use one of these two or both of these laws, F equals ma or and torque equals I alpha. And the third step is we basically use these equations to solve for a or and alpha, and then integrate a and or alpha by the way. A is acceleration. A is acceleration and alpha is angular acceleration. Integrate A alpha to get position, okay, x, y, or angular position, which is theta. So this is probably the way you were taught dynamics in 210 or as undergraduates. Now, what we'll do is we will, and I know that people don't like FPDs because you have to show the forces, and then if you don't show the forces right, then your equations go wrong. And there are a lot of things which make it very difficult to use FPDs for many people. So what we'll do is we'll instead not use Newton's laws. Well, we'll use Newton's laws, but the way we'll derive Newton's laws is through a different method. And that method is known as the Euler Lagrange equation. So that's what we'll be using in this course throughout. We will not use FBDs to derive the equations. So this is another way to find. So by the way, I should say Newton's laws basically gives us the equations of motion. Okay, to find equations of motion without drawing free body diagrams. Okay, and I'm going to lay down how Euler Lagrange equations are used first, and then we'll solve a simple problem, basically projectile motion. So that will give an intuition of how these equations are used. So here is the procedure. So first step is find the or write the position of the center of mass. Okay, so if it's a link like a pendulum, then there's a center of mass. If it's just a point mass body, like say a ball, then the center of mass is right at the middle, or that point mass is actually the center of mass. So write the position of the center of mass. So let's denote that by x c0, y c0, and note that I denoted it by 0, which means this is with respect to reference or fixed frame. Fixed frame. Okay, that's very important. Don't write it with respect to a moving frame. Okay, then differentiate. Okay, so find position center of mass, and if of course if it's a pendulum, then also find the or assume variable for rotation. Okay, for most times we'll be using theta for rotation. So in this case, let's call it theta. And so if there are n links, then there will be theta I. So I goes from 1 to n. Then find velocities. Okay, so this is as simple as differentiating xc with respect to time, yc with respect to time, and the derivative of theta I is simply theta dot I. So once you found that, next we find the what is known as the Lagrangian, and that is given by two terms t and v, where L is the Lagrangian, T is the kinetic energy. So how do you write T? Well, T is half MIVI square. Now, since we are talking about a generic system of multiple rigid bodies, what I'll do is I'll put a summation here just to indicate that we are doing multiple bodies. But if it's just one body, then it's just going to be I equals 1 plus I omega I square. Okay, where Mi is the mass, II is the inertia, Vi is speed or linear speed, and omega I is the angular speed. So in this case here, when I wrote theta dot I actually meant omega I. It's the same as omega I. So the second step is to write the V. V is the potential energy, and the potential energy is given by, these are things which depend on gravity. So if there's gravity in the problem, then the gravitational potential energy is phi I c o I. So I'm assuming that the y direction is the direction along which gravity acts. If gravity is acting at an angle to x and y, then you'll have to suitably modify this equation. Okay, and we'll come to that if you have to later on. So that's the potential energy due to gravity. And then sometimes you have springs. So that constitutes a potential energy term too. So let me write that as P equals 1 to some Q. So this is basically, there are Q springs. Then we have KP RP minus RP 0. So I'll write what these terms mean. GI is gravity. KP is spring constant. Again, that's given to you. RP and RP0 are spring lengths in stretched and unstretched position. So unstretched would be RP0, stretched would be RP. So that basically tells you how much is the potential energy stored in the spring. Okay, so what we have effectively done here is we found the Lagrangian, which is composed of two terms, T and V. T is the kinetic energy, V is the potential energy. And once you get the Lagrangian, then there is a formula which is famously known as the Euler Lagrange equation, which is used to derive the equations of motion. So the final step, third step, is to write the equations of motion. Using Euler Lagrange equations. Okay, so what is the Euler Lagrange equation? Well, it is written as follows: d dt of d of the Lagrangian with respect to q dot j, and I'll define what q is in a bit, minus dl dq j equals qj. Okay, note that, okay, I did an error here. This should have been the partial derivative and not the full derivative. So this is d dt, the complete derivative. The partial derivative is denoted as follows in the term involving dl dq and dq dot. What you do in a partial derivative is, if you take the partial derivative, there are number of terms in the partial derivative which are each functions of time. So for example, Lagrangian would have theta, theta dot, and the way you take a partial derivative is you assume one to be constant. So let's say theta is constant, you take the derivative with respect to theta dot, and then you do the same thing by assuming theta dot is constant, taking derivative with respect to theta. And so this will become clear when I do the example. So what is q? Q is the degrees of freedom. So q in this case for planar motion is going to be, or 2D motion is x, y, and theta. That's qj. And then you could have, so this is x, y, theta. This is for a system which has only translation motion along x, y, and theta. If you have a two-link pendulum, then that will not be x, y, theta, but it will be theta 1 and theta 2, and so on. So it really depends on the problem. And then q, capital Q, j is the external forces on the system. So the external forces corresponding to x, y, theta would be Fx, force in x, force in y, and the torque. So this is just, note that this is just an example. Okay, you will have to find the right degree of freedom with respect to the problem, which will be different for a projectile, it will be different for a pendulum, and so on. Okay, so this gives you equations of motion without drawing any free body diagrams. So that's why people like to use Euler Lagrange. They don't have to draw free body diagrams, because this equation gives you, essentially corresponds to Newton's law without having to draw free body diagram. So once you do this, once you take the derivative, you'll find a formula for acceleration or angular acceleration, which you can then integrate to find the position, and then you can simulate that to get the animation. There's a question. Okay, is q, this is q dot. It is not q. So let me put a note there. This is q dot. Okay, it's not q. And the q over here is just q, not q dot. Okay, so the last step, and I'll write it down quickly. I wrote it earlier, but let me put it here for completeness. The last step is to, so number 4, integrate the Euler Lagrange equation to get theta dot x dot y dot and theta x y. So you can get the speeds, you can also get the position, and once you get the position, you can then animate it, because all the animations are reliant on getting the position. Okay, Okay, so let's see how to put all these formulas into action. I'm going to do a simple problem on projectile motion example. Okay, so this is straight from your physics, a straight physics problem, but we'll add a slight twist to it. We'll actually do the problem when there is a drag force. So that will make it slightly more complex. So a projectile is, say, a distance y from the ground. So let's assume the coordinate frame is x, y, and then it's projected with a velocity v. So v x0 is the speed in the x direction, v y0 is speed in the y direction. The projectile mass is m, and there is gravity. So it's hurled from a distance y, and then you know that the projectile follows a parabolic path, but you'll see that when you have a drag force, you will not have a parabolic path, which will be clear when we do the animation. So let me use the recipe here, but before that, let me tell you what drag force looks like. So assume there is a drag force proportional to the square of speed. Okay, and then find the equation of motion, and then of course simulate and animate. So what does quadratic drag look like? The way to write the quadratic drag is, so this is the drag force. The drag force in this case is going to be, there's a constant c which gives me the drag coefficient. It's going to retard the motion, so it's a negative sign. So it's proportional to the velocity squared, but you can't just write velocity squared because the left hand side is a vector and the right hand side is a scalar. So this vector should act in some direction. In this case, we'll assume that the direction is in the direction of the speed. So v hat is a unit vector. We can write this as cv square. The unit vector is given by the vector v divided by the magnitude of v. Okay. In other words, we know that v square is nothing but the magnitude square. So we can actually cancel this. And so it's basically minus c times v magnitude times the vector v. Now this is probably the first time I've actually shown you vectors. So instead of confusing you and using this, I'm going to simplify this in terms of matrices, and we'll use the matrice to solve the problem. So if you thought this was confusing, don't worry about it. I'm not going to actually make you write vectors in this course because I've not taught it. So I'm just going to give you the force in the x direction. This is just for you to understand what quadratic drag looks like. Fx is going to be minus cx dot times x dot square plus y dot square. And Fy is cy dot x dot square plus y dot square. This comes from this equation, okay, if you want to know more. But in general, I will not give you something like this in the exam. I will just give you an equation which looks like this. That way you can use matrices instead of using vectors. Okay, so this is the form for the force. Let's try to solve for the equations of motion using Euler Lagrange method. So let's go to the next page. And I'm going to basically do this in the step-by-step fashion as I described in the algorithm I just showed you. Okay, so here's how we start. First of all, we find the variables of interest. In this case, there is no rotation. There's only displacement x, y is the position. And then you know the velocity is x dot, y dot. In this case, we don't have to do anything fancy with the velocity because the velocity is x dot y dot is good enough. In case of a pendulum, we will see that we'll have to do some more math to get the velocity of the center of mass. So here it's okay. Number two is find the Lagrangian, which is T minus V. So T is the kinetic energy that is consisting of two parts. The kinetic energy due to translation, which is 0.5 mass times velocity square, which is nothing but x dot square plus y dot square, because the velocity in the x direction is x dot and y is y dot, and when you square them, you get the velocity. And then the second part, which I wrote down in my formula, was the rotational part involving theta dot, and that is zero here because a point mass doesn't have rotational motion. There's no inertia associated with a point mass. Finally, V is mass times gravity times the height of the projectile from the ground. So that's simply Y. So we now have the Lagrangian, which is 0.5 m x dot square plus y dot square minus mgy. Okay, so question is, should that be square root of this? No, it's not the square root. That's because V is square root x dot square plus y dot square. And so V square is x dot square plus y dot square. And that's what I wrote down, used here. Okay, so once we get the Lagrangian, let's use the Euler Lagrange equation. Which states that we need to do d dt of dl dq dot minus dl dq equals qj. Okay, in this case, q is going to be two variables, x and y, and qj, in this case, qj is all the external forces, which is going to be fx, fy, or something which we wrote down earlier is c times x dot square plus y dot square, and minus c y dot x dot square plus y dot square. I'm just writing down the force in the x and y direction, which I wrote down in the previous page. Okay, so let's start computing the Euler Lagrange equations. So I need to take the derivative of L with respect to qj. So the first one is x. So I'm going to do derivative of the Lagrangian, which is this term, with respect to x dot, because I need to find derivative with respect to q dot. So that's going to be, I'm just going to write it down here. Later on, I'll just do it in my head, but right now, let me just write it down. D dx dot, that's qj dot. Lagrangian is 0.5 m x dot square plus y dot square minus mgy minus d dx dot. L is the same as before. Equals minus cx dot x dot square plus y dot. Okay, so this might seems a little bit strange for you, but just watch carefully. Here I'm taking the derivative of this term with respect to x dot. Okay, so when I take the partial derivative, everything other than x dot will be assumed to be a constant. So what happens is, keep 0.5 m. When I take the derivative of x dot squared with respect to x dot, I will get 2x dot. So think of x dot as x, for example, if you want to take the derivative of x squared with respect to x, then it's going to be 2x. And that's what I wrote down. When I want to take the derivative of y dot squared with respect to x dot, remember that y dot is now a constant because I'm taking the partial derivative. So this term is going to be 0. So that is the first part. Similarly for mgy, although y is a variable which changes as a function of time, its derivative with respect to x dot is going to be 0. And same for the second part. So this is, made a mistake here. This should be dx. Okay, so when you take the derivative with respect to x, you see that there is no term here which has a x. And so everything there should be 0. So I end up getting cx dot equals cx dot. So one more derivative and I should have the equations. Okay, so now I need to take the derivative of this term with respect to time. So the derivative of x dot is going to be x double dot. So I would have, I can cancel this 2 and this half, and so I end up getting mx double dot equals minus cx dot x dot square plus y dot square. So my equation is x double dot equals minus c divided by m x dot times x dot square plus y dot square. So if you recognize this equation, if you actually put c equals 0, which means there's no drag force, you end up getting x double dot, or the acceleration, the x direction is 0, which is what you would expect when the projectile has no drag. Okay, let's do the same thing now for the y direction, and we'll see it actually comes out to be similar to what you would get if you did it with Newton's laws. So let's set up this equation for the y direction now, because remember I have x and y for q, and I already finished x, writing the equation for x but not for y. So d dt dy dot, what I need to put here is the Lagrangian, which is 0.5 m x dot square plus y dot square minus mgy minus d of dy 0.5 m x dot square plus y dot square minus mgy equals the force in the y direction, which is minus cy dot x dot square plus y dot square. Okay, so now if you can think of taking this derivative again, it's like good practice. Let's try to take the derivative of this term, the first term with respect to y dot. Remember, I'm going to treat anything involving x, x dot, and y as constant. So the first thing I get from this equation is 0.5 m. Derivative of x dot square with respect to y is 0, plus derivative of y dot square with respect to y dot is going to be 2y dot, like before. And then when I take the derivative of y with respect to y dot, I'll have 0, because y is not a function of y dot. The y is a constant. Minus d dy, d dy of the first term, which has only x dot and y dot. So the first term is 0. This whole term is 0. You can write 0 plus 0 if you want. Minus mg times the derivative of y with respect to y is going to be 1. And so that's all equals minus c y dot times x dot square plus y dot square. Okay, and so finally we need to take the derivative of the first term with respect to time, and so we'll have, so I of course cancel the 2 and a half, so I'll have my m times y double dot, and then you have minus and minus, so it's plus mg equals minus c y dot times x dot square plus y dot square. And so I can write y double dot equals minus g minus c divided by m y dot x dot square plus y dot square. So that's my second equation. Okay, so if you sub in c equals 0, then you'll see that the equation of motion for a projectile without drag is basically y double dot equals minus g, which actually is what you would get if you did it with Newton's laws, assuming no drag. Okay, so let's call this equation 2, and the first one, which I wrote on the previous page, as equation 1. Okay, and then the final step. So this is the fourth step, is integrate x double dot and y double dot in 1 and 2 to get x dot y dot x y, and then animate. Okay, so the integration can be done in many ways. We've seen how to do it with Euler's method. We've seen how to use ODE4, okay, which is Runge-Kutta, and you don't have to write it. I already gave you the code for that. And then this time we'll do it with another solver called ODE45, which is basically an adaptive solver integrator. So what it does is it is a much efficient way of integrating the equations. It doesn't keep the time steps fixed time step. This is an adaptive, better way to say it is adaptive time steps. So it's able to do the integration much faster than Runge-Kutta ODE4 by actually taking short or big step, adjusting the time steps. And I thought you should just know how to use this, because most times people use ODE45 and not ODE4 or Euler's. Okay, so next I'm going to head to MATLAB and show you how to integrate this and how to animate the motion of a projectile. If you have questions, please feel free to ask them. So this is a projectile subjected to drag force, and you can see that the motion is not quite parabolic. It actually starts falling down, almost vertically down. Okay, so if you want to check this, well, it makes sense. Let me put, in this case, I assume that the coefficient of drag is 0.5. I'm going to put it 0, and I'm just going to increase the time just because it's only 5 seconds. Let me make it 20 seconds. So now there is no drag force, and you can expect the motion to be like a projectile, a parabolic motion. Okay, it doesn't look like it's going to actually complete its motion till it comes back to the ground. I think I need to decrease the speed a little bit. Let me just do that. So let me decrease the speed to maybe 10 instead of 100. Hold on. Let me try 5 seconds now. Okay, this is a little better. Okay, so that looks like a projectile. In fact, it keeps going, penetrates the ground, it keeps going, but it's a parabolic motion. You put c equals 0. Okay, let's get back to 0.5 and let's look at what entails in what do you need to do in order to make a simulation like this. Okay, so first of all, what I did like before is, instead of defining variables as g, m, I define them in a object called projectile. So it saves g ground, which is 0, cm inside a structure called projectile. And this is just a more efficient way of putting in variables. You do not have to do this. I do this because it just makes passing variables easy. So here you can see I pass projectile. Instead of passing g, m separately, I just pass one structure projectile, which inside which is g, c, and so on. So all I do here is essentially set up the initial conditions. Initial position is 0, velocity, initial position is 0, velocity in x is 100, uh, initial y position is 0, and then I give a certain velocity, actually launch it at pi by 3, which is 60 degrees. So that's the starting condition. Remember, this is the initial value problem, which means once I give an initial value, it will integrate the equations ahead of time to give me a simulation. And then I use this function, which is a new function now, ODE45. It actually works very similar to ODE4 in terms of how I use it. So I need to pass the right-hand side, which is basically the equations of motion I derived in my notes. So let me open that file here. So this is the right-hand side, which is the actually the right-hand side of the Euler Lagrange equations. If you remember, the Euler Lagrange equations had this term, which is CV x dot. Here, I just split it up. I made it slightly more readable by defining the velocity as square root of x dot plus y dot, and then wrote the drag force in the x and y direction. And then the acceleration is, if you remember from the notes, it's drag divided by m. And then for the y direction, it's minus g, minus drag in the y direction divided by m. So this is all it needs. In fact, ax and ay is passed back to dq dt. That's where I'm saving the right-hand side. So remember that in addition to giving the accelerations, I also need to give it the velocities, because when it's integrating, it has to not only integrate the accelerations to velocities, it also has to integrate the velocities to positions. And the way it is done is I define the velocity, acceleration, the x direction, then velocity in the y direction, and acceleration in the y direction. And that is a part of dq dt, or the equations of motion, which then go to projectile ODE45. And then you just keep, it just basically does this integration from the start, which is 0, to end, which is 5. Couple of plots. Maybe I did not show the plots. Let me show the plots. Figure 1. So the figure 1, let me run this again for the drag, and then we'll see the plots. Okay, so figure 2 is the animation, but figure 1 gives some plots. So this is the position as a function of time. This is the position, the y direction as a function of time. Velocity in the x direction. For some reason, this is showing the, this actually should have shown the velocity in the y direction. I think what I did was I accidentally clicked figure 1 before this animation ended, and that's why it showed the velocity in x and velocity, it showed the projectile instead of the velocity of y. So it turns out that if you put the drag force equal to 0, we know that the velocity in the x direction shouldn't be varying. It should actually be a constant. You'd actually see that if you put drag equals 0 and then you simulate the system. The animation code is probably much simpler than what you have done so far. It essentially draws the x position. So this is plot the x and y position. So you just keep plotting the x and y and just keep redrawing to get the figure of the ball. So my bad. This is actually the trajectory. Okay, the black line which you saw. Black line. And then this part is actually the ball shown as red. So you can make that out easily if you look at this symbol. It says red with a circle. I have a color and a face color red. So that's the corresponds to the ball, and this black line K corresponds to the trajectory. So that's it. So that's how you simulate something which involves the differential equations. We've done it for the car, but that was a first order equation. We did not have the second derivative. This equation here had the second derivative, so it involved a little bit more complex things. There are quite a few arguments which we need to pass through ODE. There were 4 of them. So it just really depends on the problem you're solving. Okay, so I think we are out of time, and I'll stop right now. I have office hours now. I'll be here till 12. So if you have any questions, you can stay online and chat. You can type or you can chat, no problem. Okay, I'll see you on Monday if you want to leave.